any questions. You know what that means? Is that means I come up with some of my own.
Can we practice a resonance structure?
Wow, you've read my mind. So here's a structure. Does it have a resonance structure? Notice there's no charges anywhere. So in the STEM Learning Center, we found out that these electrons can move. So sp2 carbons can be a part of the game. And you can't do anything with an sp3 hybridized carbon because it's got 4 bonds and they're all holding atoms and it's stuck. So another thing that can happen is electronegative elements don't mind negative charges. And here's something we can do. If those electrons jump there, these can jump up there. Here's going to be my resonance arrow. Now I'm going to have an oxygen. Still has an octet. Had an octet before. And this carbon here is sp3. It can't accept any electrons or double bonds. So there is a resonance structure.
Will the nitrogen have a plus though?
It would. Thank you. It's like I'm still down in the STEM Center. So charge is conserved. Yeah, so that top molecule, you see no charge. Down here we see, if we sum up all the charges, they go away. And nature doesn't like that so much, so the top molecule is the major contributor. Alright, so here we have a neutral molecule. We drew a one resonance structure. Let me draw one more. And sometimes students say, can I do that? And sometimes I say, yeah. So this one here, I'm going to draw this going back down to here. That's how we'd get to this structure up here. So what students sometimes say, can I do that? Can I do 2 electrons, 2 pairs moving all at the same time? So this here we might say is a concerted movement of electron pairs. We actually have 2 pairs, 4 electrons. Concerted means at the same time. So here both these moved and we got to this structure here. If I just moved that pair and didn't move that pair, we would get to this structure there. So there's really a couple types of resonant forms you deal with. Sometimes you move a positive charge around. Sometimes you move a negative charge around. Of course, that last example, we had a neutral molecule and we moved electrons around, and then we had a positive charge and a negative charge. And hopefully you're all up on your little formal charge formula. In a little while, you won't need that formula. You'll look at carbon and you'll say it normally has 4 bonds. If it just has 3, it's a carbocation. If it has 3 bonds and a lone pair of electrons, it's a carbon anion. So I almost had a nitrogen cation until I added my lone pair there. So what can this thing do? So areas of electron richness can move towards that positive charge. I'm going to move some pi electrons, draw a resonance arrow, and then I'm going to take some liberty to speed things up. So the positive charge is just moved. Well, I could draw another one where I moved that lone pair of electrons, in which case double bond would still be there. So notice what I wrote at the beginning. What moves? Lone pairs, double bonds, what atoms can play, sp2 hybridized carbons. Nitrogen's a little weird. It goes from being sp3 like hybridized to sp2 when that lone pair moves around. We won't get tied up in that. Don't worry about that right now. But all 3 of these carbons can move electrons around. This carbon isn't a player. It can't do anything. So there's the movement of a positive charge. So here is a negative charge. What can happen with this thing? So here's a good example. This carbon here is sp3 hybridized. So I can't move the electrons there and form a double bond, because then I'd have a carbon with 5 bonds. And what happens when you get a carbon with 5 bonds? No partial credit. You strike out. You can't do that. Alright, well everywhere else I see sp2 hybridized carbons. So I can take this lone pair and make it jump there. I'll cause these to jump up there. Resonant arrow. Now I'm going to take some liberty. When you see this type of thing on a Word document, it probably doesn't look like this. They probably use the bold line formula. So there's the bold line formula where hydrogens are emitted, except for that methyl group there for some reason. It could be gone. But this point right here, when I look at that, I see that there's actually 2 hydrogens. This one, there's only 1 hydrogen. And I drew it in there so you wouldn't miss it. Alright, then what can happen? These can jump in there. You can see how that's a lot more easier to draw. And if those move that way, this has to jump up like that. Get my resonance arrows.
Where did the electrons go? So there's the double bond, like in between those C's right there, and you moved it down, and it looks like it's going to by the hydrogen. Where did they go?
Right here.
So they're on the carbon?
Yep.
But they're just like a lone pair instead of a double bond?
Right. Just like right here. So here are the 3 resonance forms of this thing. And so it started out looking just like this. Here's where we left off yesterday. So depending on your solvent, like if you're in water and you add H2SO4, the strongest acid that forms is your hydronium ion. So any acid stronger than hydronium ion just makes hydronium. Same thing happens with the base. So common solvents have a limit to how acidic they can be. Sometimes that's why organic chemists don't use water. We use things where we can have stronger bases and stronger acids. And you'll see here that alcohols look an awful lot like water. At least the 1/2 just looks like hydroxide. So when you have an alcohol, it can be protonated. And now this looks just like hydronium ion. Instead of R is an alky group. That's what chemists use for alky groups. I'll have a whole special segment on alky groups. Here's an ether, as could have like a methyl and a methyl, or ethyl and or ethyl. That'll make sense later on. And the oxygen has lone pairs of electrons, and that can be protonated. And so here is the limiting acidic species that can exist in an ether solution. And then there's no type of base. And here's ammonia, and here is the alkane. And it says there's no limit. The solvent can't be protonated or deprotonated, where like ammonia can be protonated or it can be deprotonated. And we saw these species in some earlier discussions. So this might be a Chapter 16 Chem 2 review a little bit, where how does structure affect acidity and why. So the negativity trend increases from left to right and from bottom to top on the periodic table. So going across that second period there, fluorine is the most electronegative element, and carbon's the least. Here in this series, electronegativity is increasing. So now when we put hydrogens on the carbon and make something like CH4, but down here, this would be the conjugate. So here's methane, here's ammonia, here's water, here's HF. And we say acidity increases going this way due to the stability of the conjugate base. See, if HF donates a proton and you get fluoride, fluoride's nice and electronegative, and it's happy to accommodate that negative charge. Alright, if water loses its proton, protonates something, forms hydroxide, that negative charge is residing on the oxygen, and oxygen's fairly electronegative, and it's happy to do that. As we move down the line here, we don't normally think of ammonia as being acidic. You put it in water, it causes hydroxide ion to increase. It's a Uranus base, but anyway, in OChem we say, let's imagine pulling off this proton and making an acid, and then here's our conjugate base. We have a negative charge on nitrogen, and nitrogen's not so happy to have that negative charge. It really wants to get a proton and neutralize that negative charge. So here, the stability, this is the least stable thing, and I told you yesterday that this has got to be the strongest base known to man because methane, CH4, was the weakest base known to mankind. I told you that alkanes are relatively inert. Alright, so here you go. Strongest base known to mankind. A weak base, fairly weak, maybe not the weakest. I would say chloride ion is even weaker. That's because it came from a strong acid. So look, it's up at the top here. So we move down a little bit. Acids are getting weaker. Here's hydrofluoric acid. Here's the fluoride ion. So it has some base properties where put sodium chloride in your drinking water and it's still going to be pH of 7. Put some sodium fluoride in your water and your teeth will get brown spots and you'll never get a cavity. No, you don't want to do it. It'll be slightly basic. That was today's humor. So there is the electronegativity trend. So let's now look at size. We figured out that HCl is a strong acid. HF was a weak. Why is this stronger? Chloride's less electronegative. In the previous slide said the more electronegative element wants to have that negative charge. Well, now there's something a little different going on, and we're making a comparison of these going down here. Hydroiodic acid would be the strongest, or if it's a gas here, we'll just say hydrogen iodide, and we say this is the most acidic because this is the largest, and what that does is it spreads the negative charge over a larger area. And so here's $1 million word in OChem, charge delocalization. You'll hear it a lot. It explains a lot of things. So you'll notice these compounds follow their positions in the periodic table. We got methane, ammonia, water, HCl, HF, and students want to compare this and mix up all these trends. You want to just take one trend at a time. Our comparison of acidity increasing this way has to do with the increasing electronegativity of that nonmetal atom that's going to hold the negative charge once that proton is gone. Super large pKa, super weak acid. Small pKa, probably a lot stronger. And then, said the other day, normally in general chemistry we don't assign pKs because they're kind of weird here. These things completely disassociate. But here, let's just go down this row. Notice they all look similar in structure to H2O. They're all H2 and then sulfur or selenium. And the acidity is increasing here. Look, this is a smaller pKa than water. This is a stronger acid than water, and that is because the increasing size of the anion helps delocalize charge. And I mentioned this the other day when our first mechanism that you did on paper, hopefully, with acetic acid. These lone pair grab that proton. There's where the hydronium happens. And here is our base, and that negative charge can get delocalized over these two oxygens. So it gets spread out. So it's this charge delocalization that stabilizes this. Now here's ethanol, an alcohol. And it's on our big table there. This proton comes off. These electrons grab that proton. Ethanol protonates water. There's hydronium. Here's ethoxide. Ethoxide is not as stable as the acetate ion. And we see that this is a weaker acid. This is a stronger. The larger the pKa, the weaker the acid. The smaller the pKa, the stronger the acid. And then we even have that weird negative thing. If we get so small, we go past 0 on the number line. And this is because this cannot delocalize the negative charge.